Welcome. In this lesson, we're going to look at chapter 6, section 5, and it's on work. When we talk about work, work, the amount of work that's done on an object is equal to its force, the force applied on the object, multiplied by its distance. So let's think of force. We could think of our force as in newtons, N for newtons, and distance, that could be in meters, which would mean that our work, the units for work, are Newton meters, otherwise known as joules. A joule is a Newton meter. We could also have our force be in pounds and feet. So we could say if our force is in pounds and the distance is in feet, then our work is in, we say, foot-pounds. So these are two different units. We have joules or feet, foot-pounds. Now, it's easy to find a force if you just have an object and you put a force on that object over a distance. However, when you think about it, sometimes the force that we're applying, sometimes it changes over time or over distance. It changes with respect to distance. And we're going to call the distance x. So if the force actually is changing, then this is when we need to use integration. What we're going to do here is the work is actually equal to a sum of the force for any given distance, and we could call that, let's say the distance is c sub k, times the change in x. How much did x change with respect to x sub k? So we could say that k is going to go from 1 to n, and our c sub k is our x value. That's where we're starting, and then delta x is how far we push it. And as we're pushing it, the force is changing. So we have to keep adding up all the different force, the sum. We have to keep adding up the sum of the product of each new force times a little bit of distance that it traveled. Now, if we want to know, if we decide that, I'm going to move this a little bit over to the right. If we decide that, okay, we're going to calculate the force for every delta x, and this force is going to be changing as we move across our distance. So if we decide to make x very, very small, okay, then what we're going to do is we're going to take the limit as the number of work calculations goes to infinity, which means our delta x is becoming very, very small, and we keep, every time we move it just a tiny bit of x, we recalculate the force and multiply it by that little tiny bit of x. And what this gives us is integration. This is an integral. We are going to integrate from distance A to distance B of our force, which is a function of x, times delta x. Now if you look at this first bit, f of x, that is the force for any given distance. And the second bit, delta x, is how much we've moved our object with that particular force. So this is the formula for finding the the work done on an object when the force is changing with respect to the distance that we have pushed the object. Now, a good example, or pulled the object, and a good example of it is a spring. And so what we're going to do is we're going to look at Hooke's law. Hooke's law says that the force required to hold a stretched or compressed spring x units from its natural unstretched length is proportional to x. And that is, the force is equal to a spring constant times the distance that the spring is stretched. This also works when a spring is compressed. So this value k is our spring constant. It's also sometimes called the force constant. So we'll call it our spring constant. So what that means is that if we have a spring, and let's say it's naturally, our spring has a certain distance that it just sits without any force acted upon it. So here's our spring just sitting. And it has a certain length, and we'll call that length, we can say L. And if we apply a force on that spring, so that our spring is now compressed, so the coils are going to be tighter, we've compressed it, and we required a force to compress that spring. And the distance that we compress the spring, we call that x. So the force required to press that string a distance of x is equal to the spring constant times x, because the force and the distance it's stretched are directly, they're proportional, or it's direct variation. So let's, given this information, let's work on the amount of work that it would take to stretch or compress a spring. And we're going to use our equation for work such that the force is a function of the distance something is compressed, and we're going to use our equation for force with Hooke's law, where the force again is a function of how far the spring has been compressed. Okay, so let's go ahead and do our first example. Find the work required to compress a spring from its natural length of 1 foot to a compressed length of 0.75 feet if the force spring constant is 16 pound-feet. Okay, so we want to find the work that must be done. So the work that must be done, well, we're going to have to add up, this is an integral, sum up, all of our force, which is a function of our distance, times the total distance that the spring is stretched. Now, we happen to know that the f of x, well, the force is a function of x. It's equal to the spring constant k times x. So this can be rewritten as the integral of 16x, because the force, remember that work is force times distance. And work is force times distance, and this is our force, and force is changing. The force, in fact, is a function of x. And we're going to multiply that force times delta x, which is the distance. So work is, again, force times distance, and this delta x is the distance. Let me go back to the blue. And in this case, what we're doing is we're going to compress the spring from not being compressed at all to 20.25 feet, or a quarter of a foot, right? Because if we look up here, we see that it was 1 foot, and then we compressed it to 3/4 of a foot, right? So we've compressed it down to 3/4 of a foot. So actually, we compressed it 1/4 of a foot. So at this point now we can work out the calculus, okay? This is going to be equal to, well, the antiderivative of 16x dx is 16 times x squared over 2, and we're going to evaluate this from 0 to 0.25. I'm going to say 0 to 1/4. It's a little easier to work with fractions usually. And 16 divided by 2 is 8. So this is 8x squared evaluated from 0 to 1/4. And the fundamental theorem of calculus says we integrate this. Once we find the antiderivative, which is f, big F of x, not to be confused with force, it's f of b minus f of a. So let's factor out that the 8, and b is 1/4, so it's 1/4, and this is for x squared, so 1/4 squared minus, and I probably don't need to write this, but I will, just so we can see what we're doing. This is fundamental theorem of calculus part 2, because I'm squaring 0, so it's going to go away. So it becomes 8 times 1/4 squared is 1/16. 8 over 16 is 1/2. So the amount of work done is 1/2. Let's get our units right. This is 1/2 foot pounds, or pounds per foot, or feet per feet pounds. Okay, so let's see, that is the work that it's done to compress the spring. All right, let's try another problem. And here, let me box our answer. There's our answer. It's 1/2 of a foot-pound to compress that spring 1/4 of a foot. Okay, so now let's move on to, oops, let's see. Oh, here, I've done this problem again. Okay, let's move on to our next problem, which is also a spring. Okay, a spring has a natural length of 1 meter, so let's highlight that, that's its regular length, and a force of 24 newtons holds the spring stretched to a total length of 1.8 meters. So the first question is find the spring constant. So we're saying that, well, we happen to know the spring constant. When we're calculating spring constant, we know that the force is equal to the spring constant times the distance the string is stretched or compressed. So from this we can calculate x by dividing both sides by k, and we can calculate k, our spring constant, by dividing both sides by x. So the spring constant is F divided by x. Well, our force is 24 newtons, and it's divided by 1.8 meters. And let's see if we take let's see, it has a natural length of 1 meter, and we have to look at how far it's stretched. So this is not, let me fix that, because actually what we're doing here is we're not stretching at 1.8 meters. The spring has a natural length of 1 meter, and it's stretched to 1.8 meters. So here we're stretching the spring. So the change in distance that we've stretched it is 0.8 meters. There we go. So, and if we don't have a calculator, we can say that's 24 newtons times, well, 8.8 is 8 over 10, which is 4/5, but we're actually dividing by 4/5, so we multiply by the reciprocal, 5/4, and of course the meters are still down here, and this becomes, let's see, I'm going to get my red, and 4 goes in once, and 4 goes in 6 times, and we get 30. That's our spring constant. 6 times 5 is 30, and the units are newtons per meter. That's our spring constant. So this is our first answer. We just found the spring constant. Okay, let's move on to the next question. How much work will it take to stretch the spring 2 meters, stretch it 2 meters, beyond its natural length? Okay, so this is going to require an integral. The work it's going to take to stretch the spring from 0 to 2 meters. And what we're going to do is we need to find what is f of x, what is the force with respect to how far we stretch the spring, times how far we stretched it. Okay, it's because work is force times distance. So you go from 0 to 2, and well, f of x is equal to k, the spring constant, times x. That's the force. This is how far we stretch it. And we happen to know that k is 30, so it's 30 x dx, and now we can integrate. That's going to be 30 times x, not to the first, but the second, x squared, divided by 2, and we're going to evaluate this from 0 to 2. Well, 30 divided by 2 is 16, so it's 16, and we're going to, once we get this, we're going to, let's see, 30 divided by, there's a mistake. 30 divided by 2 is 15, there we go. And then we have x squared, which is 2 squared, minus 0 squared. And that works out to be 15 times 4, which is 60. And the work here is joules. This is newtons per meter, so that's joules. So let's box this answer. So we have the work done. And finally, how far will a 45 Newton force stretch the spring? And this brings us back to Hooke's law, because we know that the force is equal to k times x. And we want to know how far, so if we were solving for x, we divide both sides by k, and x is equal to the force divided by the spring constant. Well, the force is 45 newtons, and the spring constant, which we've already determined, is 30 newton per meter. We end up with 45 divided by 30, which is 1.5 meters. Notice the units are meters because I divided by the reciprocal, which means multiply by its reciprocal, and we got meters. Okay, so that's our next problem finished, and we're going to move forward and work on another problem. This next problem is a bucket lifting problem. So let's start with, let's see, let me draw a bucket. I've got a little bucket down here. Here's the top of the bucket. Let me zoom in on the bucket. The bucket's going to be leaking. So, not leaking, excuse me, we're going to lift the bucket. So here's our bucket. Let me turn my tool on so I can make a nice looking bucket. And we're lifting the bucket up. And we're lifting it up with a rope. So let's bring this down. We're going to lift the bucket up, and let me throw the rope in. Here's our rope, which is attached to the bucket. Copy that. All right, so here's our rope. Got it kind of wrapped around the bucket, and we're pulling this rope, and we're going to be pulling it and tugging on that rope to lift the bucket. So what we have here is we have a 5-pound bucket, so the bucket is 5 pounds, and it's lifted from the ground into the air by pulling on a rope. It's a 20-foot rope, so we're going to lift this bucket 20 feet up. 20 feet up, and the bucket weighs 5 pounds. The rope also has a weight. Let's see, the bucket is 5 pounds. The rope is a 20-foot rope. We're lifting it at a constant speed, and the rope has a weight. It's 0.08 pounds per foot. So we want to know how much work is done to lift the bucket all the way up so that all the rope is pulled up. Well, the work done, the total work done, is going to be equal to the work done to lift the bucket plus the work done to lift the rope. The work done to lift the bucket, well, the force is constant. It's equal to the force of the bucket multiplied by the distance that we'll stretch it, that we'll pull it, I'm sorry. The force of the bucket is 5 pounds, and the amount that we lift the bucket is 20 feet. So the work done to lift the bucket is 5 times 20, so that's 100. And the units are foot-pounds. Okay, so this is the work done to lift just the bucket. Now we're going to look at the work done to lift the rope, and this is where it gets a little bit interesting. Because we're going to lift this rope. The rope has a weight. Now, let's write this over here. The force of the rope, R, is equal to, well, 0.08 pounds per foot. Well, how much the rope weighs depends on how much rope we have. So let's say the amount of rope we have is X. So the force of the rope is 0.08 X. And of course, X is in feet. And I should put that in so you can see that the units go away. Let me put that in. X is X feet. And I did that so that you can see that our feet will cancel out, that this foot cancels out this foot. Go back to black. And so we end up with 0.08 X pounds. That's the work, that's the force of the rope. I'm going to move this down. I need to, or maybe I can move it up. Let's move it down here to the bottom. Okay, there we go. All right, so the work done to lift the bucket, well, we're going to have to integrate. This is an integral, okay? And we know that the force that used to pull that rope is a function of the distance. As a matter of fact, it's the force to pull the rope is 0.08, right, times the distance that we pulled the rope. Well, if we're going to integrate, let's say we decide to integrate from 0 to 20 because it's 20 feet of rope. This is important. I'm going to zoom in on this. I want to focus on this integral that we're doing. And I'm going to pull it down. Let me pull it down just a little bit. So this is the work for this is R. That's an R for rope. The work for the rope. Okay, the first part, this, what I'm hitting here is this is going to be the force. All right? Now, the force is 0.08 times however much rope is there. Well, for integrating, where X is going to go from 0 to 20, well, initially, there's 20 feet of rope there, but if we subtract X, well, when X is 0, which is at the very beginning, then 20 minus 0 is 20, and the weight of the rope will be based on a 20 feet of rope. But when we get to the end, when X ends up equaling 20, we end up with 20 minus 20, which is 0. There's no rope left. I hope that you can see what's going on here, is that this part here, this actually represents the weight of the rope given how much rope is there as we integrate from 0 to 20. Initially, when X is 0, all the rope is there. When we finally get to 20, well then all the rope is gone. When we get to 10, as we're integrating from 0 to 20, well 20 minus 10 is 10, and half the rope is there. Okay, let me get rid of it. So that's the force. And we're going to have to multiply that force times the distance that we've pulled it. And so that's a little bit of X, a little bit of delta of X. So that's the integral that we have to solve here. And at this point, if let me move this up, we're solving this. We can certainly factor out, let's see, the work due to the rope. We can pull out the 0.08, And we can go ahead and take the antiderivative of 20 minus x dx. Well, that's going to give us 20x minus x squared over 2. And then we have the fundamental theorem of calculus, right? We're going from 20 to 0. So fundamental theorem of calculus part 2 says this is equal to 0.08 times. We're going to put 20 in, f of b, 20 times 20 minus 20 squared over 2 minus f of a. There's no f of a. I can't, if I put a 0 in, that becomes 0, that becomes 0, so I don't really have to put that in. So I can end it right here. And so it becomes 0.08 times 20 times 20 is 400 minus 20 squared is 400 divided by 2 is 200. Let's see how much room I have here. So this ends up equal to 0.08 times 200, which is equal to, let's see, 0.08 times 200 is 16. And this is 16 foot-pounds. Let's put a box around this final. Oh, this is actually, let me highlight that. That's the weight, that's the work done to pull the rope up. So if we want to find out what is the work done to pull the rope and the bucket up, we are going to have to take 100 foot-pounds plus 16 foot-pounds, and our final answer is 116 foot-pounds. And let's box that. That's our final answer for this problem. Here we have it. So we've done 2 spring problems. We've done a bucket problem. We have one more problem left to do. Let's get down to our very last problem. We have a conical tank. A conical tank is filled with 2 feet, is filled within 2 feet of the top with olive oil weighing 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? So let me go ahead and draw our tank. So here's the top of the tank, and we're going to have our tank come down. It's conical shaped, all right? And I have to actually give you the function of this. Here's our conical tank. Let me straighten that out. Looks something like this. And this is our x-axis, and this is our y-axis. We have to put make ourselves relative. And this is the top of the tank, and the height of this tank is 10, but we're only filled to a height of 8, right? Because we're within 2 feet of the top. And what we're going to have to do is we're going to subdivide, cut the tank up into discs, so that the height of the disc is delta y. And our actual disc, let's take a look at, here's one of our discs. Copy this and paste. So here we have our disc. Its height is delta y. It has a radius of x. Let's see if the radius is whatever x happens to be. And its volume is the surface area of the top, which is pi r squared, times its height, which is pi x squared times the height, which is dy. All right? So that's the volume. And we're going to take each one of these, and we're going to, each one of these discs of olive oil and pull them to the rim. All right? Now we have to look at the function. That is the function that is this line right here, which is the line that goes through the origin. That's the side of our edge of our tank. And there's an equation for this line. It goes up 10 over 5 for this particular problem. Okay? So this is the function y is equal to 2x. Or if we want to write as a function of x, we would say x is equal to 1/2 y And now we're going to start to get to work here on our integral. All right? Because what we want to do is we want to add up the weight. All right? We want to integrate. And what we want is the weight of each cylinder, the weight of each disc, times the little bit of delta y that it has been moved. I'm going to move this. Let me move this up here. We're going to work our way down. So we're going to integrate from, let's see, we want to integrate from 0 to 8, because remember, we're only 8 units high, okay, only 8 feet high. And what we want to do is we want to take the disk, which is pi x squared dy, that's the volume of the disk, and the weight of the disk, we're going to multiply it by, it is 57 pounds per feet cubed. Okay, so we just multiply by 57. So it's 57 pounds per feet cubed times the number of feet cubed, so that's the weight of the disk. And then we want to multiply that by dy. Where am I having an issue here? We have our dy already in there, don't we? We do. We have it. So the dy actually is part of the disk. So let's move that over here, and we're going to have to. Okay. So what we have here with that dy and the pi x squared, that is the volume of the disk, and we multiply it by 57, and that is how many pounds per unit volume. So what we have here is actually the weight, and we have to lift it a certain amount. How much are we going to lift it? That's what goes here. This is the amount that we're lifting each one, and we're going to lift it from 10 minus y. The 0 to 8 is y, okay? So when we start at 0, we're going to lift it 10. The very bottom disc down here, the very bottom little disc down here gets lifted a full 10 all the way up. Now, when we get, say, the halfway point, this disc is the halfway point, going from 0 to 8, we're going to be at 4. It would be 5. 10 minus 5 is 5, so we're going to lift that only 5. We get to the very top disc, and I guess it would be 4, isn't it, that we lift it? We lift the 4, 6. We get to the very top disc, when y is 8, we're going to lift that 10 minus 8, which is only 2 feet, because the very top disc is only 2 feet from the rim. Okay, move this in. So this is our equation that we are going to use to find the work that's done. And so I can pull out, let's see, I can pull out the 57 pi, right, because they're constants. And then, oh, I have a little bit of, let me figure this out. I have a little problem here, and I'm going to fix it in a minute. Look what I have left. When I pull out the 57 pi, I have x squared times 10 minus y dy, and what you'll notice is my variable of integration is x. So I've got a bit of a problem right here. Let me get the red, because I need to write that x squared in terms of y, right? And I happen to know, if I look over here, x is actually equal to 1/2 y. So since x is 1/2 y, x is y over 2, I want to then square it. So x squared is actually equal to y squared over 4. So I'm going to have to put that in. So what do I end up with? Well, I can pull the 4 out. It's a constant, right? So this is going to be equal to 57 pi over 4 times the integral from 0 to 8 of y squared times 10 minus y dy. At this point, you're all set to integrate, and I'm going to leave this for you to work out. I'll give you the answer, and you work it out and make sure that you end up with the same answer that I have. But when you find the antiderivative and use the fundamental theorem of calculus, your answer should be that it's approximately equal to 30,500 561 foot-pounds. Let's box that answer. So go ahead and work on the problems in this section in my math lab. This is Chapter 6, Section 5. Do the 6-5 homework and make sure that you're able to do all the problems that we did together in this section.